I will just take a few minutes to introduce our excellent panelists, right? Yan already, I think Keith did a wonderful introduction about Yan. I just want to add a few more things. He actually is the key reason, one of the key reasons that I joined NYU Shanghai. I don't know if you mentioned that he is a member of National Academy of Engineers. But sadly, one fact though, I'm sorry that Facebook is banned in China. So the only building that's legally access Facebook is here. As you show that, you probably see that many of our guests are having two hats. They are world-class scholars as well as institutional leaders. And our next distinguished guest, Dr. Shen, he is the CTO of IBM China, and also the head of the research of China, and guest professor at several universities, and his research interest kind of overlaps with what I did before in system research in general. So I'm just going to be brief. Professor Fan, chair professor in Princeton, and also he runs the Institute of Data Science in Fudan. And he is world-class statistician. I'm not going to read all the fields. And editor of a number of leading journals and so on. And he's from Fudan. My friend and colleague, Mai, he was my Microsoft Research Asia colleague, and also world scholar, particularly in optimization, control theory, sparse coding, and so on and so forth. He practically runs the School of Information Science and Technology in Shanghai Tech, which is only 20 minutes from here. And last but not the least, our very distinguished Professor Xiaojin. He is neuroscience and also Associate Vice Chancellor for Research at NYU Shanghai. A number of distinguished awards, and he is also world-class scholar in neuroscience. Just to give you an idea how good these people are, I ran the statistics 2 days ago. I'm going to hide the names. Those are the citations by our guests, right? And all tally up, 134,000 citations, right? So I'm going to just have one more slide to set things up, and I just pass my baton to our guests. Okay. So many of you here probably wonder, this is a very interesting time, right? So you see this beast called AI is at our doorway, and you're excited and probably nervous as well. But as it turned out, our fantasy about AR has been long-standing. I think this is in our gene, right? We want to replicate ourselves in biological ways or not. And, we all have this very complex love and hate relationship with the human being, ourselves. I think no one says it better than Shakespeare. Thyself is also sweet, but also cruel. Now, I just want to refresh your memory. The fantasy about AI has been long-standing. Even at the very beginning, when Turing was conceiving his machine, there was a way. And in mid-50s and 60s, there was another wave. 1996, IBM's Deep Blue beats the world champion in chess. And that same year, the Go was thought as the only game that's unbeatable by machine, and they played it in space. And about 20 years later, we have AlphaGo that beats human. So these two events spaced by 20 years. Let me just play a very short video clips for you to get an idea.
It's a tool to widen the horizons. But newspaper headline writers wanted to believe there was more to these machines than that. authority. Alan Turing, a brilliant mathematician, always saw computers as much more than mere number crunchers. The vision Turing had of computers even led him to design one. Pilot Ace, the only more or less complete machine that survives from that era, was based on that design. But Turing hoped to use it for more interesting things than arithmetic.
1946, which was a long time ago. Because this is where computers started, electronic computers started. This is one of the first stored program computers. It was designed by a man called Alan Turing, who was in fact a British mathematician. He was involved in cracking codes in the war, in the Second World War, cracking the German codes, yes, in the war.
Turing's ideas on computers went back even further than the war. In 1936 he had published a paper on an abstruse mathematical problem. In that paper, written a full decade before computers were built, he wrote about computing machines and demonstrated theoretically that one such machine could in principle do any logical task a human could do.
So you have seen on the newspaper wave of electronic brain, right? So that was the first thing that people thought about it. And then this one.
Do you know what? Even Hollywood took up the issue.
He's up on the roof feeding the pigeons.
No. Do you know what he's doing here?
What?
He's trying to replace us all with a mechanical brain. He's under special assignment to his eye to see if MRAC can be adapted to this department. That means the end of us all.
Hey, calm down. No machine can do our job.
That's what they said in payroll. Movies like Desk Set revealed the conflicting emotions computers stirred up in society. While many people viewed them with fear and disdain, others thought they represented progress, the future, a relief from tedious tasks.
Good girl.
Not surprisingly, the staunchest advocates for computers were the computer manufacturers, like IBM's Tom Watson Jr.
A lot of people call these machines giant brains, and whenever I hear the term, it makes me shudder. Because they are giant tools, they're certainly not giant brains. And if you have good tools, you're upgrading them, not downgrading them.
So that was in 1950 when IBM's and other big companies' machine come to start to replace work for them. Okay, so you can see the conflicting emotions and projections, and which is sort of replicating in this era. So I think the central theme I want this panel to answer, I'd love to pick their brain, is what's different this time around. And let me begin by asking Yan and Dr. Shen, the two industry representatives, because we had this question earlier about startups, but the big companies that control the larger surface where you can channel the technology to the people and back and forth. So I think I'd like to know your opinion, not only from your company's point of view, but also the industry-wide. Okay, thank you. Do you have the?
So I mean, certainly, I have a built-in microphone, so that works. So certainly the history of AI going back 60 years is a succession of disappointments, really, because people thought that computers were going to be intelligent automatically because they were able to implement logic and everything. And it didn't happen. It turned out that the complex things for a computer are the things that are relatively simple for humans, like perception. We don't even think of perception as being an intelligent task. It turns out to be one of the most challenging ones for computers. On the other hand, simple logic reasoning is relatively easy for a computer. Arithmetics is relatively easy. Mathematics is relatively easy. Computers now can essentially give you the solution to an integral. We thought this was kind of a higher function of that only smart people could do, but it turns out that's relatively simple. The same is true for playing chess or Go nowadays. So what's happened in the history of AI is that as soon as the problem is that AI is a moving target, because as soon as a problem is solved, it's not considered AI anymore. So back in the 50s, compiler technology was considered AI. It was automatic translation of natural language specification of instructions into machine language. That was considered part of AI. Tree search, pathfinding, all that stuff that was considered part of AI, you still see this in classical AI courses nowadays. But they're really just algorithms. What's different this time is that all of AI is based around machine learning, around learning. And that's one big qualitative difference with sort of previous approaches to AI, which is the reliance on learning. And that's been a battle of multiple decades between the proponents of learning-based AI and the proponent of more kind of logic-based AI, where the knowledge is entered by hand, essentially. There are still people working on this. This is not a part of AI that has completely disappeared. But I think it's certainly a big difference that's happened over the last few years. The other difference compared to the previous waves of AI is that now there is actually a very large market around AI. Companies like Facebook, Google, Baidu, Tencent, Microsoft, etc., IBM, of course, Amazon use AI on a daily basis, billions of times a day, to do everything they do for us. So Alibaba is the same, and Huawei. I mean, everybody now is getting into AI. Intel, NVIDIA. The reason is because it's used on a very, very large scale for everything we do. A lot of those companies would not actually work without AI. Facebook certainly could not exist without current AI technology. So that's a big difference in the past, where you had kind of a wave of interest for AI, but the industry that were built around them were relatively small. They still exist, but they're relatively small. That's what makes it different.
Okay, so in the past many years, we have seen a lot of technical progress, right? Machine learning, not to mention that. And also the whole technical stack, right? Computers are getting much faster, right? You use FPGAs, you use GPUs to do accelerations for machine learning, all those things. Plus, we have big data. So everything we're talking about is in the context of big data that provides a context for us to train the systems. Having said all this, I actually feel one of the biggest differences is that you see the applications of cognitive or AI technologies in vertical industries. Personally, I think the success of AI will depend on the continuous business success. Without that, we will not be able to sustain this kind of hype. 5 years later, when we have a talk like this, you will have only half of the people like what we have today. So for AI, for many people, AI stands for artificial intelligence. At IBM, we actually use AI to stand for augmented intelligence. So what that really means is you apply cognitive or AI technologies in the big data context on specific industries. If we look at the things that are important to us, like environmental protection, renewable energy, health, you get to use AI technologies to solve the problems we have today. So here I see two things. One is we may not be able to make a computer today that is as mature as an 80-year-old kid today from all aspects. However, we can make a computer that is an expert in a very specific area to solve a specific problem. So we get to choose those areas where technologies today, as well as technologies we forecast that will exist in the next few years, can help solve those problems, number one. Number two, some of these problems, computers or AI systems are good enough to solve maybe 90% of the problems. However, the last mile, the remaining 10% will be very, very difficult to resolve. Then the challenge is how can we combine human beings together with existing technologies so that we can provide end-to-end solutions for our existing customers to solve real problems. Plus, you get to build an ecosystem to get to figure out the business model. Without that, it will be very difficult, in my personal view, right, to drive the industry forward for the next couple of years. Thank you.
Very good, very good. So I take it, for those students who hope to have AI to write essays for you, you will be disappointed. You have to wait a long time. And I think that you guys are optimistic that this time around, the AI winter probably will not come for a while. Is that accurate?
Well, there's a lot of hype, certainly, around AI these days. It's caused, certainly hype is one of the factors that has killed AI in the past, where people overpromised and never delivered. And so when that happens, the people who are paying for the technology or the research, the investors in the startups, the funding agencies that fund the research become less excited about it, and funding dries out. And so there's also a natural evolution of the field where there is an exciting phase where there's a lot to explore, and there is a very quick growth of all the different topics and applications that people think of. And then after a while, it saturates. It becomes less exciting. It becomes more of a normal business, more mature. So that necessarily creates kind of a saturation in the amount of investment, a decrease in the amount of investment, and more of a kind of a steady business. So the question is, is the wave going to disappear? So is AI going to disappear? I don't think so. That's the big difference with previous waves. Is the hype that we see at the moment going to diminish? Yeah, of course, no question. But because of the promises of the transformation of society by AI, I think we're going to still see a lot of excitement for quite a long time, and for self-driving cars, for personalized medicine, for virtual assistants, for all kinds of technologies of this type.
Just one comment. So we are talking about the hype, where the hype comes from. One fact is that it comes from those high-profile projects like AlphaGo, like IBM's Jeopardy, Deep Blue, right back to 20 years ago. So all that is good. However, if we cannot solve real problems like healthcare problems, environmental protection problems, we'll have a problem. But the good thing is that we see AI technologies are being deployed to address some of those issues. That's what keeps people optimistic.
So I guess the development of core idea technologies happened at a time probably the application doesn't even exist, and that happened to deep learning and so on and so forth. It was a very long time that people prolonged and did a really ground preparation for this revolution to happen. So let me now turn the focus to our scholars, because I think it so happens all of you represents the core areas that very close to, at the core of the future, in my mind, artificial intelligence. Statistics, right? Optimizations of core neuroscience. I would add a system, which I worked on before. People have heard of MXNet. That's a deep learning platform now picked up by Amazon that I work with my students on. But just leave system aside. I'd like to have your opinions from your perspective, particular fields, and also comment on the general thing of how we have these drives that's going to be long lasting. Okay? Any one of you want to lead?
This is a very good question, so thank you for having me here. I see most of the audience here are very young, right? You really hold in the future. Future always defined by younger generation. But from my perspective, there's really this is really very exciting time. Is really an interface among many disciplines, right? Some from statistics that we model. The problem of that from the society to the optimization that actually help deliver this to the system that actually really implement the idea. So today. We see a lot of excitements like in, let's say, deep learning networks. And to me, as a statistician, is really, a class, very special class of non-parametric model. This has been very well implemented and approximated by the deep neural networks. And certainly there's a lot of, theory underpinning those, why this specific, how good this specific class of function can approximate. So there's a lot of really theoretical research that we probably can probably do on these aspects, and only when we understand the fundamental, what is the limitation and what is the strength of this deep neural network technology, that we can apply these to many very interesting problems. So for example, being a person having done for so many years on big data, modeling, and we always say about, let's say, precision medicine, precision marketing, and so on. So for a class of problem that is not image-based, can this be done very well by neural network? And we do not know that. So there's, a lot of machine learning AI problems drive a lot of modern theory and methods. And I thought it's a very exciting period for all of us to define what is the frontier of the future, and the frontier of the future can be, can be better served when we combine very well the theory with application. Only technology alone, we certainly have a limitation. We are really just blind ourselves and trying to, to test our luck. So I think the future is really belong to the audience here.
That's a very excellent point. I think Jan would agree with me that we do not really know very much about how deep networks and so on and so forth. So we'd love to have, statisticians to provide bonds and so on and so forth, to have a better idea, a better lens, so to speak, of what's going on. Thank you. So, Yi?
Yeah, Professor Frank talked a little bit about the future. I think that indeed about I've taught a course at Shanghai Tech last semester about deep learning. Also, I think two of the most important sort of open question about deep networks. One is in the statistical front, is that how the learned network, why it generalizes, right? So the second sort of big open understanding about the neural network, open problem about network is actually the optimization. What are the guidelines to design better networks? Right now, it's a lot of work. We're seeing very, very ingenious design, but they're very much trial and error, right? We don't really know what the mechanism to ever build more efficient, more powerful networks. And so in that, I see, I just want to comment a little bit on the history, right, from a optimization point of view. In the past 10 years, I've been studying a little bit on a branch of the signal processing or data processing, data analysis is on the compressive sensing. So there we saw a very, very strange phenomena, right? When we try to scale up the algorithms to solve sparse coding, and that Yang talked about, and also or the structural optimization. If you try to estimate solve an inverse problem and try to estimate some unknowns with certain structures. And we actually found out if you once we try to scale this up to higher dimension or larger data sets, the kind of optimization procedure that become more and more efficient, more and more powerful, actually the older algorithms. The algorithms that invented in 1990s and 90s were slower or less scalable than that was in 80s. 80s is slower and less scalable than the 70s, and so on and so forth. Well, hence put us in a very interesting perspective, right? Is having computers not necessarily helping us designing better algorithms, right? Having faster algorithms. So because in the past, back in old days, when the computer is slow, when the memory is precious, that forced people to think about when you live in a resource-limited environment, make you think about the method, efficiency of your method. And which goes a little bit against right now, there is a little bit sentiment in the deep learning literature, I think, is that we try to build an even bigger, deeper network. And that as an optimization person, I'm a little bit hard to accept that because it's been, historically, the holy grail of optimization is try to have an algorithm that converges fastest, right? Takes fewer iterations and the simplest iterations. Each iteration is simple and the number of iterations is very, very few, right? And so personally, I do not necessarily agree that, build a bigger and deeper network is the way to go. That brought me to two small stories, right? The short stories that related to the sparse coding and also optimization of deep networks. Back in 2000, I think 2010, I was at 10 or 11, I think I was at Microsoft. I had a conversation with John Platt. I mean, he was the machine learning manager of the machine learning group at Redmond at the time, but now he's joined Google, right? John Platt. So he was doing the deep learning for speech recognition, was really trying to convince me that something is really exciting about the deep networks. I said, I don't know much about it, the deep learning at the time. I just was exposed to it. He said, no, it's very, very simple. You are doing exactly the deep learning. I said, what? He said, well, if you look at the algorithm you guys designed for sparse recovery, right? If you look at the phase tower, we are doing the architecture. If you look at each iteration, right, exactly the same sequence operations, linear operator plus thresholdings and so on. And so that was very interesting. So that actually led into this unfolding perspective of looking at deep networks. So if you look at the deep network, each layer, they're sort of emulating what we do in optimization in each iteration. So you can call each iteration is a layer. Okay. And also I was really excited to see actually the new RES network when it first came out. And Yang has also mentioned that's very efficient. But okay, now from optimization person, that's great because everybody does constraint optimization. If you're students, open your, go back to open your textbook, right? You will see that's exactly how you update Lagrange multipliers, right? The identity map plus a term correct the errors of the object function. So it's basically the architecture that we have explored through deep learning that tends to have more efficiency or more effectiveness actually has been there, explored it, or designed, or discovered in optimization algorithm that people have to use to improve the algorithm in solving constraint optimization or optimization that try to look for structured solution, right? So I think this is a resource you can get inspirations to hopefully in the future. Of course, we still don't know too much about some of the more diverse neural networks, but certainly I think the understanding of optimization will provide us new perspective of how to make a neural network, design a neural network more efficient and more effective in the future.
Okay. So I guess the upshot is, starvation, resource starvation drives better optimization. That's accurate. So to my student, my lecture time will be reduced by 10 minutes. Next, we have class, okay? So by the way, these two guys are both from Berkeley. You can kind of see a pattern from them. So I think humans are intelligent in part because we have very scarce resources. Our ancestors didn't have cell phones. We probably have just one shirt to live for a whole year. So let me turn this to Xiaojing then, from neuroscience point of view. Why don't you?
Thank you for including. Thank you for including me in this panel. So I do neuroscience, but a special kind of neuroscience. Actually, I build mathematical models of neural circuits in the brain. So I don't know if you have ever had a chance to hold in your hand a human brain. It's really a 3-pound meat, right? So it's wet. It's a biological system with chemicals, receptors, genes, etc. Right? So if we want to understand the intelligence in our head, we do experiments, and then we try to combine experimentation with modeling, with theory, and you build mathematical models, which of course could serve as a bridge with AI. I want to say two things. One is that AI, revolution that Jan just described to you is really amazing. It's real revolution, I think, in the society. It's not going to go away. It's influencing even how we do computational neuroscience these days. So me and with my group and my colleagues now use training recurrent networks for machine learning to apply to try to understand how the brain works, how the real neural circuits works. So it's going from AI field to neuroscience. Jan also mentioned the other direction, right? So the deep network, in some sense, was inspired by what we learned about the visual system in the brain. I know for a fact that the Japanese pioneer that you mentioned, Fukushima, really came up with this idea because he was in the same office as Keiichi Tanaka, who is a well-known visual neuroscientist. And so I think that the interactions between neuroscience and AI is going to be really interesting, exciting in both directions. And in some ways, that could be crucial about kind of continued progress in this field. I guess you got the sense from Jan's talk in the second half, in the later part of his talk, that really so far, right, the evolution has been, you could say, mostly about perception. And the questions that Jan talked about later in his talk are more about higher cognition, right? Problem solving, working memory, decision making, evaluation, judgment, etc., and language. So I want to just mention one thing that people distinguish intelligence in two different ways. One is called a crystallized language. That's basically about knowledge, right? So what's the capital of New York State, right? What's the capital of, Jiangsu province? So this is the kind of knowledge that you learn. This is called a crystallized intelligence. The other kind of intelligence is called a fluid intelligence. That's more about, solving the problem on your feet, right? Flexibly, smart way. So I guess you could say that today's AI, you mentioned logic operations, calculations are actually rather easy for computers. Perhaps the hardest part is the fluid intelligence, right? How we really can flexibly process the same information depending on your behavioral goals, depending on what you're thinking, depending on the context. How do you process really language in the same way, in a context-dependent way? Those are the kind of problems that belong to fluid intelligence that we don't know a lot about. And incidentally, neuroscience also is only just now moving to study the real brain mechanisms of cognition. So that I see a very exciting ground for the back and forth between the two fields.
Very good. Originally I wanted you guys to challenge each other, but I feel you guys so polite. But do you want to have questions between yourself before I have the audience ask questions? Do you have things you want to ask to each other?
Well, I heard Yi said that he didn't quite believe that adding layers was a good idea. That's pretty controversial nowadays.
Well, in optimization, we know that we try to cut iterations, right? If you look at at least mathematically, the type of operator we do in equity descents and algorithms that we really try to cut the iterations. In fact, there's another perspective. I was at Caltech, talked to some of the folks from optimization. So the design of neural networks is rather dual mathematically to the traditional objectives in design the optimization algorithms. When we design in optimization, we try to design a algorithm that works for a class of problems. But in learning, we care about the instance. And so in optimization, we let the iteration runs to death. Here and in learning, we try to, let's say we stop at the 50 iterations. But I want this 50 iterations the most effective, not solving one sample. Optimize this 50 steps for an ensemble of samples of this particular object function, of this inverse problem, or this nonlinear mapping. And we train that with ground truth. So hence that there is, in fact, even neural networks by essence is trying to optimize the optimization path for a particular instance of problem. So that actually changes, at least that's one perspective to look at how we make things more efficient. The goal is really trying to make our algorithm or networks, no matter how you call it, or optimizing algorithm, more efficient. I think that will be at least a very important effort in the future of, I think designing of. Maybe right now it seems that we have unlimited data, unlimited computing, right? We can just make NVIDIA happy, right? Just buying extra GPUs and also having poor students label more and more data. But that will have to come to a stop, or when they eventually will have, hit a brick wall, and we have to come back to see how to best utilize our resources. Right?
I followed this up, and I was fascinated by your talk, especially about this adversary network. It's quite cool. So when you optimize, you have a cost function you try to minimize, for example. In this case, you actually have two networks. Each one has its own cost function, right? So basically, the question to you is that in the field of optimization, is this a new idea that you actually have not just one thing to optimize, but you have several things to optimize? They interact with each other? Right?
No. This
one
is
is kind of responsible for optimization of the other in some
yes.
sense?
So that's actually not new. I mean, in fact, the GAN network actually is really utilizing the game theoretical framework, right? It's really a minimax, trying to minimize the error I made, against the worst possible cases, and has been utilized. This is actually a sort of game theoretical approach to look at, but also two players. But potentially in the future, you can even generalize to multiple players.
So for example, if you have two functions you want to optimize.
No, it's one object function.
Well,
but two
that's
players.
the thing. My understanding is that you can't have more than one.
You actually
and they may not be compatible. Right? So that's more interesting.
Multi-objective optimization. That's another.
So let me just add a little bit to from statistical or mathematical perspective. Right? So I believe, it's really a bias variance trade-off. Right? So the deeper the network you have, the better you can class you have, the better you can approximate the original problem. But then the less stability you'll learn, parameter you can estimate. So I believe that for each problem, for each specific class of problem, for a given sample size, there must be an optimal number of layers that actually will turn out the best solution. And that actually really is, well, there are certain, criterion could get used, but there's also a lot of those like a technology trial and error that actually should get involved. That's my view is really there must be many, but not too many layers that you can use.
So, yeah, you want to add something? Or?
Yeah, there's several formulations of GANs. One of them is when there is a single function and two sets of parameters. One are the parameters of the generator, and one is the parameters of the discriminator. And then you minimize with respect to one, maximize with respect to other. And that's basically consists in finding a saddle point of a single function. But the formulation I showed, you actually have two completely separate functions. They're coupled, but there are two separate cost functions. And when you try to minimize both at the same time, you get into kind of an equilibrium. You cannot minimize both at the same time without actually solving the problem you're interested in. So that's where you start to get into those game theory type situations. And it's kind of a new paradigm in machine learning. So almost all of machine learning can be reduced to either optimization, simple optimization, or optimization under constraints. So for example, you can reduce backprop to a problem of optimization under constraints. You write a Lagrange function that has constraint that says the output of a layer should be equal to the input of the next layer, essentially. That's what it comes down to. And backprop just comes out of this in three lines of math. It's very simple. So, but since the 1960s, essentially, since Duda and Hart, 1974, all of machine learning is based on minimizing some sort of objective function. In adversarial training, you're doing this kind of Nash equilibrium, optimizing two functions that fight against each other, or in a special case, you can reduce it to finding a saddle point of a single function. And this is really new, and it breaks all the all the intuitions we have about what we should do about machine learning. We're in a situation right now where when people try to use GANs and it doesn't work, they have no idea why, including people who are quite experienced with them. So there is a lot of conceptual understanding of GANs that we don't have that we need to work on. There's a recent paper, I think in the last 6 months or last year, there's been a flurry of papers of different variations of GANs. There's InfoGAN, WGAN, EBGAN, stack GANs. I mean, there's all kinds of different flavors. And the reason there are different flavors is because none of them actually works completely. People haven't found a recipe for building and training GANs that works every time. It's a little bit the same situation that neural nets were in the late 80s and early 90s, where there was no really kind of good recipe to make them work. And so some people would implement their own program for backprop and try it out, and they would have made some stupid assumption that basically would make it not work. And that's part of the reason why people abandoned neural nets, because it was so finicky. It was kind of a bit of a black art to be able to make them work. Now you can just download a piece of code and people have worked out those problems for you. and dropout is implemented, and batch normalization is implemented, and Adam or Adagrad is implemented, so you don't have to deal with all those problems. But for GANs, we haven't found a recipe yet. So that's what makes it interesting, in fact, because it's mathematically interesting and challenging, and it's a new set of problems, and it works amazingly well when it works, but sometimes it completely fails, and we don't understand why. That's what makes it interesting, in my opinion.
I guess we humans also fight against ourselves too in our mind. If we do that too much, we just go insane. Anyhow, so I see a small, with your hammer, you see everything as a nail kind of thing, because you see a bias variance, you see optimization, and you see nets. But I think, overall, I think we got to work together. I think that's the point. And instead of going to 50 iterations, we have 5 questions. Make your question count, okay? Let those guys sweat, impress them. So let's open the floor.
Hello. So my question is for all the panelists. What are some of your concerns regarding the ethics of AI, and how do you think it should be regulated?
Yeah, so I'm part of I was instrumental in getting something called a Partnership for AI off the ground. This is a group of industry players, so it includes IBM, Amazon, Microsoft, Facebook, and Google, and then Apple joined recently. And there is a board that includes members of non-governmental organizations, civil liberty organizations, for example, in the US, and member of the academics, like economists, sociologists, etc. And the purpose of this group is to discuss ethical issues related to AI, issues of safety. So this is not really the discussing issues of, are super intelligent robots going to take over the world, Terminator style. This is not the kind of stuff people are worried about today, because the technology doesn't exist, because it's not entirely clear what the interesting questions there. It's more, how do we design procedures, for example, that make sure that the AI systems we deploy are safe? So, for example, how do we test a self-driving car? The self-driving car is going to be a trained system. How do we make sure it's safe? It's somewhat of an unsolved problem. The same way it was sort of an unsolved problem in the 1920s of how to build an airplane that was safe, right? So people kind of learned this over the years, and we need to do this with AI as well. There's another issue which is bias. So whenever you train a system on data, the system reflects the bias in the data, and sometimes that has very bad effects. So you start seeing startup companies offering products that influence people's lives in ways that are really important and dangerous, and making choices about their health, or deciding whether a criminal is going to be a repeat criminal, for example, which is very difficult choices you have to make. And if those choices are made by a machine, you want the machine to be built in such a way that it doesn't have the systematic bias that are built in the data. If you have a system that recognizes faces in the crowd to determine if someone is likely to commit a crime, you don't want this thing to be deployed everywhere and have 20% error, because you're going to put 20% of your population in jail. So, I mean, there is questions like this that are very very difficult, that need to be discussed in the open. It's not something that each individual company or research group can do by itself. It has to be discussed in the wider society. And it's not entirely clear what the regulation should be, if there should be any. It's a little too early to tell.
But the panelists want to comment. I think this is a very important question.
Yeah, actually, I agree with what Yan just said, right? Just make 2 points. One is whatever challenges we have, right, for legal, for all those issues, pretty much very similar to what we had before when we had other revolutionary technologies. I think that's common. Maybe this time it's more revolutionary, number one. Number two, I personally feel sometimes we are a little bit too scared. Some of the questions, yes, you get to discuss in an open environment, but sometimes the questions we're discussing, to me, sound like when we are talking about immigration to the Mars, we are saying, do we need family planning over there, right? Yes, you do, but it's way too early.
I think it's just like any technology, right? So it's always like could be a double-edged sword. There's always a good side you can use for the benefit of society, but also could have if it's abused, it could have very very dire consequences. I think one particular, especially I think in the data-driven age or data-rich age right now, I think also with the tools of AI now that there are open sources. There are also that the computational platform can easily accessible to average Joe. And also all the data, if not regulated, could cause us a very, very serious privacy breach. I'm very glad to know that U.S. already taken. I'm hoping that effort will become one day will become international. Also influence places like China, where I think the breach of data privacy is actually pretty outstanding. Right, there's all this fraud, and that we see. Gets if your personal information and gets just or on our mobile phone, or daily purchases, usages, financial record, everything. Your personal information gets abused, and if it's at a massive scale, and if there are criminal could use the tools to analyze data and come up with schemes much more dangerous than before, and so that could also cause us issues. And of course, hopefully with the help of government and also the industry, have to put some kind of regulations to this. I mean, that will help with the situation. Otherwise, any technology can be used for the bad things, if not regulated.
Anyone else wants to comment or move on? So, I wrestled with this problem myself as well. And I don't have an answer, but I made a decision. That is, I want to understand and research how AI works. Because unless I know how it works, I don't know how to deal with it. Okay, so for my students, I encourage you to be part of their students and study their relevant fields, because that's how you get connected to the future. Okay, next question.
I want to ask what specific social or commercial goals that you are trying to achieve, and also how do your work benefit yourself besides income and reputation? Thank you.
We all work for ego, right? That's
well, there's two answers to this really. For speaking for myself, I think. For me, working on AI is something I've been interested in since I was a child, essentially. I was fascinated by a bunch of different scientific questions. There's basically three big scientific questions over time. One is, what's the universe made of? The second one is what life is all about, and the third one is how does the brain work? So if you are interested in science, most of what you do has to do with one of those three questions. And at heart, I'm really an engineer. And so trying to solve the third scientific question, how the brain works, is really how do you build a brain? I think Richard Feynman, the famous physicist, said once that you don't understand something until you build it yourself. And I kind of believe in this concept. So AI for me is a way of understanding the principles behind intelligence, whether it's human intelligence, animal intelligence, or machine intelligence. What are the underlying principles? That's a scientific question. Then there is a technological question, which is how you implement it, how you get it to work. You have to get it to work, because if you have some abstract idea about how the brain works and you're not able to actually reduce it to practice, you can be fooling yourself. And so there is an empirical side to the sort of engineering approach of actually making something work and making it. And if you're going to make it work, you have to measure its performance, which means you have to have a task, and that task better be practical. So that's kind of the motivation behind this. That's what's driving me. Now, of course, there are societal impacts of what we can do, and hopefully those societal impacts will be beneficial. So hopefully we're going to do things like building self-driving cars, which may reduce the number of deaths on the roads. I don't know what the numbers are in China, but certainly in the US, it's something like 30 or 40,000 deaths per year on the road. We'll be saving lives. Medicine is going to have also a big impact. Perhaps with those methods, will help cure more people, detect diseases before they become too bad, or have new ways of treating chronic diseases like diabetes and things like that. So I think that's going to have clearly a big impact. There might have an impact. There might be impacts on education as well. It's a whole spectrum of things. And then there are kind of side effects which may be initially negative, but hopefully in the long term positive. For example, the fact that we're going to have self-driving cars and self-driving trucks is going to put a lot of people out of job. Of course, new jobs are going to be created that are more, better than the old ones. But in the meantime, when people, when the skills evolve because technology evolves, and people are kind of left behind because their skills are kind of outmoded, and they need to kind of learn the new skills that are required by the new industry, you're going to have what's called technological unemployment, where a part of the population is going to be in training to try to kind of catch up with technology. As technology accelerates, there's going to be more and more of those people, and societies will have to organize themselves to take care of those people. So some countries, I think, are well prepared to do this, others not particularly well. There are countries that have a tradition of social safety net that I think are prepared to deal with this issue, and there are other countries that are much more like the jungle, where you don't survive if you don't fight, and those may be less prepared for what's coming. So that's something that's very worrying. A lot of economists have been commenting on this question, and very famous economists like Jeffrey Sachs, for example, at Columbia, and various other people who said the quick acceleration of automation brought about by AI is going to cause the social contract to have to change. It's going to have a huge political implication. You've seen that recently. In fact, some people interpret the recent results of the elections in the US as a consequence of the fact that the whole branch of the population in the US was basically abandoned by the economy. And so that has very dire consequences. We are seeing today a increase in wealth inequality in almost every country around the world, but particularly in countries like the US and China, where the wealth inequality is very, very large. You have a small number of very rich people and a very large number of essentially poor people. And it's an unstable situation. And technology, unless the societies are organized to deal with this, technology emphasizes that problem. And so that may create new political movements that are against this. And so people may turn against AI because of this, right? This is something that all of us who are technologists here will have to deal with at some point, that people might think of us as being the bad guys. We're not the bad guys, we're producing the technology. It's the question of how it's being used and how society takes advantage of it. But those are questions that people here who are interested in sociology or politics will have to think about. Economists certainly are thinking about this.
Anybody? Well, we have to close very soon, but go ahead.
Yeah, I think any innovation, in my humble opinion, serves two purposes, or at least one of the two purposes. One is to help us understand better the world we live with, and also ourselves, human beings. The second thing is to develop technologies that help us change the world, and AI happens to satisfy both.
I basically concur with everything that has been said. I do think that, at least in my mind, it's a bit still in the future. It's not happening yet. I think people right now blame globalization for the economic problems for a fraction of population in the US. But the fact is that technology, in fact, is a bigger factor than globalization, right, for the economical situation in the US, certainly. But I also think that we do need to start thinking about those issues, social issues, ahead of time, because everything takes time to change. So it is very important. I think, people could have thought about implications about globalization earlier, for example, right? That'll be very helpful. So I just want to segue this message to our students a little bit because, as you have heard, right, some original ideas, at least in deep learning, deep network theory, actually, occurred very early on, about 25 years ago, by pioneers like Jan LeCun. So what I'm saying is that we are a big society. You can be interested in just jumping to industry right away, but you can also be interested in more fundamental questions, right? That would take a longer time. But if you're interested in more fundamental breakthroughs, I encourage that some of you, just take that route, take that trajectory, thinking about the deeper problems that will also, potentially lead to bigger breakthroughs.
Thank you. So let me just conclude that there is always going to be a small number of rich people, and let me just say I don't care about them. And there is a small number of students that are lucky here, and I hope this lecture has been inspiring to you. Thank you very much.